Welcome to Science Pills. Um, Imagine a microscopic rocket, right? Like a rocket that is so overloaded with energy and so just fundamentally structurally compromised that it catastrophically fails in midair.
Right, just completely falls apart.
Yeah. But it doesn't just blow up all at once, which is what you'd expect. Instead, it violently ejects one of its main thrusters.
Mm.
And then, I mean, a fraction of a microsecond later, the remaining battered fuselage explodes again.
And it ejects two more thrusters simultaneously.
Exactly, just to reach like some totally desperate semblance of stability. So today we have a deep dive that is going right to the absolute ragged edge of what is physically possible in the quantum realm. We're taking you to a place in nuclear physics known as the Proton Drip Line.
And it is arguably one of the most fascinating frontiers in modern science right now, because when we talk about the proton drip line, we are really looking at the extreme limits of atomic stability.
The edge of the cliff.
Right, the absolute edge. We are examining nuclei that are so densely packed with protons and so deeply unstable that the fundamental forces of nature are basically engaged in this relentless tug of war.
And the atom is actively losing that war.
Very actively losing, yeah.
So to guide you through this, we have an incredible stack of sources today. I mean, we're pulling directly from peer-reviewed papers published in Physical Review Letters and Physics Letters B.
Both really heavyweight journals.
Oh, totally.
Yeah.
Plus, we have these detailed experimental presentations from the Institute of Modern Physics, the IMP, and some really comprehensive theoretical overviews on nuclear symmetry from preprints.org.
Right.
And our mission today, for you listening, is to basically take all this super dense, cutting-edge data and extract the core mechanics of how reality behaves when you push it to the breaking point.
Because the sources, they detail the discovery of these highly exotic atomic nuclei that just, well, they do not decay in the traditional ways we've always observed in standard radioactive material.
Yeah, this is not normal radiation.
Oh, no, not at all. They instantly blow apart by spitting out 3 or theoretically even 6 protons at once. And that completely forces us to re-examine the structural integrity of matter itself.
Yeah, so we are going to look specifically at a newly discovered isotope called Aluminum-20. And guys, this isotope is literally breaking the established rules of nuclear symmetry.
Shattering them. Really.
Yeah. And reading through these papers, I just kept coming back to one overriding question, like, we all know protons repel each other, right? Positive repels positive.
Basic electromagnetism, yeah.
Right. So how can a nucleus even exist, even as this fleeting quantum state, when it is so ridiculously overloaded with positively charged protons? If the electromagnetic repulsion is that overwhelming, shouldn't it just, refuse to form in the first place?
Well, you are hitting on the exact tension that drives this entire field of study. To understand how it forms at all and why it violently falls apart, we really have to look at the interplay between the electromagnetic force and the strong nuclear force.
Mm-hmm.
But we won't just look at what is happening inside Aluminum-20. We're going to explore the precise mechanics of why this specific explosive decay sequence is basically forcing physicists to fundamentally refine our mathematical models of the strong nuclear force itself.
Which is huge. But before we get into how Aluminum-20 is breaking the rules, we probably really need to establish what the rules actually are, right?
Right, we need a baseline.
So the sources talk extensively about isospin symmetry. And if we're going to understand why a 3-proton explosion is so weird, we have to know what a stable, symmetric nucleus is actually supposed to look like.
Oh.
So let's map out this territory. What exactly is the proton drip line, mathematically speaking?
So to map the drip line, you have to sort of picture the chart of nucleids in your head.
Okay, got it.
Think of it as this sprawling landscape of every single possible combination of protons and neutrons. Now, running right down the middle of this landscape is what we call the Valley of Stability.
Like a literal valley on a topographic map.
Exactly. And that's where you find the atoms that make up our everyday world, carbon-12, oxygen-16.
The stuff we're made of.
Right. In that valley, the attractive, strong nuclear force perfectly balances out the disruptive Coulomb repulsion of the protons. So everything is happy and stable.
But if you start hiking out of that valley, like if you just keep forcing extra protons into a nucleus, you're basically climbing a very steep, very unstable hill.
Precisely. Because as you add more protons without adding neutrons to sort of space them out, the total Coulomb repulsion, which is the electromagnetic force trying to tear the nucleus apart, it increases drastically.
And the strong force can't keep up.
Well, the strong nuclear force is incredibly powerful, right? But it has a very short range.
Oh, right, okay.
It only operates effectively between neighboring nucleons, so the protons and neutrons right next to each other. But the Coulomb force, the electromagnetic repulsion, that has an infinite range.
Wait, so every proton in the nucleus is pushing away every other proton, no matter where they are inside it?
Yes. Every single one repels every other one. So eventually, as you add more protons, you reach a mathematical boundary where the strong force simply cannot bind even one more proton.
And if you try?
If you try to add it, it instantly just drips right out of the nucleus. It won't stick.
Yeah, literally just drips off.
Yeah. And that absolute cliff edge, that boundary, is the Proton Drip Line.
Okay, so crossing the drip line means you're dealing with quantum states that are just fundamentally unbound.
Right.
But the sources suggest that physicists actually have this surprisingly accurate rulebook for predicting exactly where this cliff edge is, based on that thing we mentioned, isospin symmetry.
Yes. And this concept actually dates all the way back to Werner Heisenberg in the 1930s.
Heisenberg, as in the uncertainty principle guy.
The very same. Heisenberg and later Eugene Wigner, they realized something really profound about the strong nuclear force. Because, we're used to thinking of protons and neutrons as distinct, different particles because of their electric charge.
Sure. Proton is positive, neutron is neutral.
Right. But Heisenberg proposed that as far as the strong nuclear force is concerned, protons and neutrons are actually identical.
Wait, really?
Yeah. The strong force basically treats them as two different quantum states of the exact same particle, which we just call a nucleon.
So I want to make sure we are totally clear on this, for the listener too. The strong force is completely blind to electric charge. Like, it literally doesn't care if a particle is positive or neutral.
That is exactly the core of isospin symmetry. They form an isospin doublet. So if you could just magically switch off the electromagnetic force, a proton and a neutron would behave completely indistinguishably inside the nucleus.
That's wild.
The strong force binding a proton to a proton is exactly the same as the strong force binding a neutron to a neutron, or, a proton to a neutron. It's all just glued to the strong force.
Okay, it's almost like subatomic forensics. Or picture this like a perfectly balanced seesaw, right?
Yeah, a seesaw.
Yeah, imagine on the left side of the seesaw, you have 13 kids wearing red shirts. We'll call them the protons. And you have 7 kids wearing blue shirts, the neutrons. Now, on the right side of the seesaw, you completely flip the ratio. You have 7 kids in red shirts and 13 kids in blue shirts.
Right, the exact opposite.
So isospin symmetry dictates that because the strong force, the gravity of our seesaw, treats all the kids exactly the same, regardless of what color shirt they're wearing, both sides of that seesaw should balance perfectly. The internal mechanics of those two scenarios should be literally identical.
Yes, exactly. And in nuclear physics, we call those two flip scenarios mirror nuclei.
Mirror nuclei.
Okay, so nitrogen-20, which has 7 protons and 13 neutrons, is the mirror partner of aluminium-20, which has 13 protons and 7 neutrons.
Okay, they're the seesaw kids.
Right. According to the foundational math, their energy levels, their quantum states, and their internal structures should mirror each other perfectly.
But there has to be a catch, right? Because we can't magically switch off the electromagnetic force in the real world.
No, we cannot.
So the side with 13 red shirts, the 13 protons, that side has way more electromagnetic repulsion pushing them apart than the side with only 7 protons.
You are absolutely right, and that is exactly where the predictability comes in. Because the beauty of your seesaw analogy is that the only mathematical difference between those two mirror nuclei should be the predictable effect of that electromagnetic force.
Oh, because everything else is identical under the strong force.
Exactly. And physicists can calculate Coulomb repulsion, the electromagnetic force, with extreme precision. It's a well-understood math. So if you take the structure of the neutron-heavy nucleus, which is usually quite stable and easy to study in a lab.
Like nitrogen-20.
Right. If you take that and you mathematically subtract the calculated Coulomb energy, you should get the exact structure of the proton-heavy mirror nucleus, Aluminium-20.
Wow. Okay, so it's a mapping tool.
Very much so.
If we can measure how much energy it takes to pull, say, a neutron off nitrogen-20, the neutron separation energy, we can just run the isospin equations,
right,
factor in the Coulomb difference, and basically predict exactly how much energy is going to take to pull a proton off aluminium-20.
Yes.
We can predict the entire blueprint of an atom before we even create the thing.
Exactly. And, this symmetry is foundational to our understanding of the universe. It's not just a neat trick. The equations governing isospin symmetry give us this critical parameter known as the symmetry energy of nuclear matter.
Okay, why does that matter outside a lab?
Well, this isn't just about abstract math. The symmetry energy literally dictates how densely protons and neutrons can be packed together under extreme gravitational pressure.
Wait, like inside a neutron star?
Precisely like inside a neutron star.
Yeah.
The crust properties, the overall radius, and even the tidal deformability of a neutron star spinning, thousands of light years away from us. All of that is directly governed by the symmetry energy equations we derive from these tiny microscopic interactions on Earth.
That is mind-blowing. So essentially, what happens in these invisible little atoms dictates the shape of dead stars.
It does. And so, if our understanding of isospin symmetry fails, when a nucleus is pushed to the extreme edge of the drip line, it means our macroscopic models for the most extreme objects in the universe are also missing a really big piece of the puzzle.
Okay, that raises the stakes significantly. It means we can't just trust the math, right? We have to actually test the seesaw.
We do. We have to literally build these impossible, overloaded atoms right at the edge of the cliff and see if they actually behave the way Heisenberg and Wigner said they should.
Which perfectly leads us to the experiment itself. The physical, messy reality of creating an atom that desperately does not want to exist.
Right. And building an entirely unbound atom is, well, it's an exercise in managing extreme kinetic energy and massive statistical improbabilities.
I bet.
The sources detail this multi-year effort utilizing the fragment separator at the GSI Helmholtz Center for Heavy Ion Research, which is over in Darmstadt, Germany.
Okay, and we really need to emphasize the sheer violence of this process, right? Because it's not like a high school chemistry lab where you're just carefully bonding elements in a beaker.
Oh, no, not at all.
You are creating an isotope that decays in a fraction of a microsecond. Yeah. You can't just capture Aluminum-20 in a vacuum chamber, put it on a desk, and hit it with a laser to study it.
No, it would be gone before you even blinked. You have to create it mid-flight, traveling at relativistic speeds, and basically catch the shrapnel of its explosion as it flies past you.
That's insane. So how do they actually do it?
The methodology is brilliant. It's a multi-stage beam sequence. So they began with a primary beam of magnesium-24 ions, and magnesium-24 is completely stable. It's normal.
Okay.
They injected this stable magnesium into their synchrotron and accelerated it to a kinetic energy of 591 MeV per nucleon.
Let's contextualize that number for a second.
Yeah.
591 mega-electron volts per nucleon. And it has 24 nucleons. So you're talking about massive total kinetic energy. This beam is moving at what? Roughly 80% the speed of light?
Roughly, yes. It is carrying phenomenal momentum. So they take this relativistic beam of magnesium-24 and they slam it into a primary target block made of beryllium. And this block is about 4 grams per square centimeter thick.
Okay.
When the magnesium-24 hits the beryllium target at that incredible speed, it undergoes what's called a fragmentation reaction.
Fragmentation, meaning it just completely obliterates the nucleus upon impact, like the abrasion-ablation model, right?
Yeah.
Where the beam basically shears off pieces of the magnesium nucleus, leaving these highly excited, shattered remnants flying forward.
Yes, it literally physically rips nucleons away. And out of the millions of collisions happening in that block, a vast shower of all different kinds of isotopes emerges from the back of the beryllium target.
A subatomic debris cloud.
Exactly. So the scientists then use a series of very powerful dipole magnets, which is the fragment separator itself, to bend the flight path of this entire debris cloud.
Oh, because magnets affect moving charges.
Right. Because different isotopes have different masses and different charges, they bend at slightly different angles when they pass through a magnetic field.
So they're sorting them.
Exactly. By tuning the magnets perfectly, they can filter out almost everything else, isolating a very specific, rare, neutron-deficient isotope, magnesium-20.
Okay, so they've successfully generated a secondary beam. Just to recap, magnesium-24 hits the wall, breaks apart, they magnetically sift through the wreckage mid-flight, and pull out a clean beam of magnesium-20.
You got it.
But magnesium-20 still has 12 protons, and we are trying to build aluminium-20, which has 13 protons, so they just smash it again.
They do. They direct this secondary beam of magnesium-20 into a second beryllium target.
Oh, wow.
This one is thinner, about 2 grams per square centimeter, but here's where the physics gets incredibly nuanced. They are no longer looking for a violent fragmentation reaction this time.
Why not?
Well, if you just rip a neutron off magnesium-20 violently, you get magnesium-19. To get aluminium-20, you need to transmute a neutron into a proton without altering the total mass number of the nucleus. You need the mass to stay at 20.
Oh, I see.
So they are looking for something called a charge exchange reaction.
Ah, I noticed this specifically in the IMP presentation data. They highly highlight this charge exchange reaction, but they also admit that this specific reaction pathway has a microscopic cross-section compared to a standard knockout reaction.
Yes, microscopic.
For those maybe less familiar with the physics jargon, a smaller cross-section means the statistical probability of this reaction actually occurring is incredibly low, right? You are going to get vastly fewer successful hits, which means your data set is going to be tiny.
Very tiny.
So why rely on such a rare reaction? Why not just use a beam of something slightly heavier and just knock protons off it the hard way?
That is a really critical methodology question. While a knockout reaction is statistically much, much more common, it fundamentally alters the mass, and it injects a massive amount of chaotic energy into the system.
Like using a sledgehammer.
Exactly. If you want to study the very precise low-lying ground states of aluminium-20, you need a reaction that is incredibly delicate, relatively speaking.
Okay, delicate at 80% the speed of light.
Right, relative delicacy. So in a charge exchange reaction, the magnesium-20 projectile basically just grazes the beryllium target nucleus, just a grazing pass. And during that microscopic fraction of a second as they pass each other, they exchange a virtual pion.
A pion.
Yeah, a pion is a meson that carries the strong force between nucleons.
So they are literally trading quantum properties mid-flight.
Exactly. The exchange of that pion flips the isospin state of one of the nucleons. So a neutron in the magnesium-20 essentially flips into a proton, while a proton in the beryllium target flips into a neutron.
Oh, yeah.
So the total atomic mass stays at 20, but because the proton count went from 12 to 13, the element instantly changes from magnesium to aluminium.
It's essentially a quantum sniper shot.
That's a great way to put it. It is statistically very rare, but it is the only way to cleanly populate the specific low-energy structural states of aluminium-20 that they desperately needed to measure.
Okay, so the sniper shot lands, the neutron flips, and for a fleeting microsecond, aluminium-20 actually exists.
It does.
But as we established, it's way beyond the drip line. It is unbound. It instantly violently explodes. So how on earth do you actually record data from something that ceases to exist almost the exact moment it is created?
Well, because the decay happens in flight. Right after the target, the researchers deployed an array of position-sensitive silicon microstrip detectors just downstream of that secondary target.
Okay.
Now, these aren't cameras in the traditional sense. They are highly calibrated semiconductor sensors, and they don't look for the aluminium-20 itself that's already gone. They look for the decay products. They're basically hunting the ghost.
Hunting the ghost. I love that. So when aluminium-20 decays, it violently sheds 3 protons, and it leaves behind a slightly heavier core, neon-17. So these silicon strips have to catch all 4 of those individual pieces simultaneously.
That is the absolute requirement, yes. The detectors measure the energy deposited by the particles, which physicists denote as delta E, as they literally strip electrons while passing through the silicon.
Okay, so they get the energy.
Right. And they also measure the precise time of flight, how long it took to get there, and they track the magnetic rigidity, or B rho, of the particles as they pass through subsequent magnetic fields.
Let's pause on that term magnetic rigidity because it's so vital to how they identify what they actually caught. What is B rho actually telling the researchers?
So magnetic rigidity is essentially a measure of a particle's momentum divided by its electric charge.
Okay.
When a charged particle moves through a magnetic field represented by B, it travels in a curved path. The radius of that curve is rho.
Right, basic electromagnetism again.
Exactly. Now, a highly energetic, heavy particle that has a small charge will curve very little. It wants to keep going straight. We say it has high rigidity.
Like a bowling ball.
Exactly. But a light particle with a high charge will curve very sharply. So by precisely measuring that curve, the detectors can definitively identify whether a hit was a proton, a neon-17 core, or just some random background noise from the collision.
And the IMP data specifies they used a 4-fold coincidence trigger.
Yes.
Meaning the data acquisition system only actually recorded an event if it detected the neon-17 core and 3 separate protons hitting the sensors within the exact same incredibly tight time window.
Correct. If they only saw 2 protons, they threw the data out. They needed all 4 pieces. And by capturing the specific energy, the charge, and the trajectory of all 4 pieces in that tiny coincidence window, they can invoke the conservation of momentum and energy.
Oh, to rewind the clock.
Exactly. They mathematically run the clock backward. They use a technique called invariant mass kinematics to reconstruct the decay vertex. That's the exact point in 3D space where the aluminum-20 nucleus broke apart.
Wow. And this leads us to a really crucial validation step for the whole team. Because before they could publish a paper claiming they saw a 3-proton explosion, they had to prove this incredibly complex reverse-engineered mathematical detector rig actually worked.
Right? You have to prove your tools aren't lying to you.
So they had to look at what happens right as we step over the proton drip line, just before we jump completely off the cliff into the crazy stuff. And according to the sources from physics letters B, the experiment first confirmed the existence of Aluminum-21.
The discovery of Aluminum-21 was the necessary proof of concept for the whole operation. Aluminum-21 has 13 protons and 8 neutrons, so it's slightly less extreme than Aluminum-20.
But it's still unbound.
Yes. It is the very first isotope of aluminium ever observed beyond the Proton Drip Line. So successfully detecting and mapping it was a monumental achievement in its own right. It totally validated their entire methodology.
So we've crossed the line. The atom is officially unbound. What did they actually see when they reconstructed the ghost of Aluminum-21?
So the researchers were able to observe two prominent states of Aluminum-21, which appeared as these really distinct resonant peaks in their data. They achieved this by analyzing the angular correlations between a magnesium-20 core and a single emitted proton.
So 1 proton for this one.
Right. And through this mathematical reconstruction, they determined the exact mass and the proton separation energy of Aluminum-21 for the absolute first time in physics history.
Amazing. Now, you said angular correlation. Let's dive into the mechanics of that, because it's not just a buzzword. It's the absolute core of invariant mass kinematics. How does measuring an angle tell you the mass of an atom that already exploded?
Think about the conservation of momentum. When a parent nucleus like Aluminum-21 decays, it breaks into a heavy magnesium-20 core and a light proton. In the rest frame of that original parent nucleus, the momentum of the core and the momentum of the proton must perfectly cancel each other out.
Because momentum is conserved. They basically push off each other.
Right. Because of this, they don't just fly apart randomly in any old direction. They diverge at specific angles relative to each other, and they carry specific, quantifiable amounts of kinetic energy.
It really is subatomic forensics, like arriving at the scene of a high-speed car collision. You didn't actually see the impact. The event is completely over.
But you have the debris.
Right. But if you find the bumper 50 feet that way at a 30-degree angle and the windshield 20 feet this way at a 10-degree angle, you don't just guess what happened. You use vector mathematics.
Exactly.
By measuring exactly where the pieces landed, how much they weigh, and the angles of their trajectories, you can calculate backward to find out exactly how fast the car was going and how heavy it was at the precise moment of impact.
That is a perfect analogy. That is exactly how invariant mass kinematics works. You are reverse engineering the quantum energy state of the parent object by meticulously summing the momentum vectors of all the debris.
Man, math is cool.
It really is. In the case of Aluminum-21, they calculated the relative energy spectrum and found clear, distinct peaks. This allowed them to map the low-lying energy levels of this entirely new isotope. And it proved definitively that their silicon microstrip detectors and their mathematical models were capable of extreme precision.
Okay. So they proved they could catch the ghost. And that meant they were finally ready to analyze the main event. Because if Aluminum-21 is just dipping a toe over the drip line, Aluminum-20 is taking a running leap into the abyss.
It's a completely different beast.
Right. Aluminum-20 has 7 fewer neutrons than stable aluminium. The ratio is completely skewed. This is where the physics gets truly exotic.
Exotic is definitely the right word. Aluminum-20 is entirely, completely unbound. It doesn't just decay by shedding a single particle. It violently sheds 3 protons to ultimately become neon-17.
3 protons. When you visualize the Coulomb barrier, the idea of a nucleus having enough internal energy to violently eject 3 protons, it's just staggering.
It is. But the precise mechanism of how those 3 protons actually leave the nucleus is what elevates this from a neat observation to a top-tier physical review letters publication.
The how is the big deal.
Exactly. The researchers measured the decay energy, which physicists call the Q value, for the 3-proton emission of the Aluminum-20 ground state, and they pinned it at 1.93 MeV.
Okay, 1.93. And the uncertainty margins on that measurement are incredibly tight, right? The IMP data listed as plus 0.12 and minus 0.10 MeV. So they are very confident in that 1.93 number.
Very confident. But the crucial breakthrough was analyzing the angular correlations of those 3 protons. They discovered it is not a simultaneous democratic burst of 3 protons at once.
It's not a three-way tie.
No, it is a highly structured, sequential 1 proton, then 2 proton emission.
Hold on, I want to trace the microseconds of this decay step by step because the energy pathways here are just fascinating. So it starts with the Aluminum-20 ground state. It's immensely unstable.
Yeah.
So step 1, it ejects a single proton.
Yes. Almost instantly, the Aluminum-20 ground state emits 1 proton. We call the energy of the specific first ejection Q sub E, and it was measured precisely at 1.7 sienes MeV.
Okay.
Now, when Aluminum-20 loses that 1 proton, it obviously changes elements. It drops down to an intermediate state, specifically becoming the ground state of Magnesium-19.
But wait, if Magnesium-19 is sitting there after ejecting the first proton, it still only has 7 neutrons to balance its 12 protons.
Correct.
It's still missing neutrons. It shouldn't be stable either. Does it just sit there as a new isotope, or is it instantly decaying again?
You've hit the nail on the head. It absolutely does not sit there. Magnesium-19 is itself radioactively unbound. It simply cannot hold its structure.
So it falls apart immediately.
Right. So we immediately transition to step 2. The Magnesium-19 intermediate state undergoes a 2-proton emission. It spits out 2 more protons at the exact same time.
Wow.
The total energy released in the second stage, Q sub 2p, is 0.76 MeV. And only after violently losing those 2 additional protons does the nucleus finally settle down into the bound, stable ground state of neon-17.
Okay, let me go back to the rocket analogy from the intro to picture this. The main body of the rocket is Aluminum-20. It fails, and it explosively ejects a single booster rocket. That's the 1.17 MeV proton.
Right.
But the remaining rocket body, the Magnesium-19, is still horribly unstable, structurally compromised, and just tearing itself apart. So a fraction of a microsecond later, it violently blows off 2 more boosters at the exact same time before the final battered payload, the neon-17, finally achieves a stable trajectory.
It perfectly captures the sequential cascading failure of the system. It's a fantastic analogy. And we really need to highlight the historic nature of this specific decay pathway.
Has this never been seen before?
Not like this. Aluminum-20 is the first ever observed 3-proton emitter, where its 1-proton decay daughter nucleus is itself a known 2-proton radioactive nucleus.
Wow.
We have documented single proton emission extensively in the past. We have even documented simultaneous 2-proton emission, where the protons often exit as a correlated pair, sometimes called a date proton.
Right.
But seeing a parent atom spit out a single proton, only to create a daughter atom that immediately spits out 2 more simultaneously. Confirming that exact sequence observationally had never been done until this specific experiment.
It is basically a cascading chain reaction of instability. But as groundbreaking as confirming a sequential 3-proton explosion is, the sources suggest that the actual amount of energy released during this process is what really has theoretical physicists alarmed.
Oh, definitely.
And this brings us right back to the rulebook we established at the beginning, isospin symmetry and the seesaw.
This is exactly where the narrative shifts from a brilliant experimental discovery to a fundamental theoretical crisis.
A crisis.
A bit of one, yeah. Because we established that the total measured decay energy, the Q value for the 3-proton decay of Aluminum-20 is 1.93 MeV. Now, if we actually trust the rules of isospin symmetry, we should be able to look at its mirror partner, Nitrogen-20, and predict what the decay energy of Aluminum-20 should have been.
Right. Nitrogen-20 has 7 protons and 13 neutrons. Aluminum-20 has 13 protons and 7 neutrons. It's the exact same nucleons on the seesaw, just swapped. And Nitrogen-20 is a bound, well-understood nucleus, right?
Exactly. So when theoretical physicists take the known neutron separation energy of Nitrogen-20, calculate the expected Coulomb repulsion differences for the 13 protons, and project that math onto Aluminum-20, the equations state unequivocally that Aluminum-20 should have decayed with significantly more energy than 1.93 MeV.
So the math fails.
The math fails. The energy measured in the GSI detectors was substantially lower than what the fundamental equations of the strong force predicted it would be.
The seesaw is fundamentally broken.
Broken. And reading through the Gamow shell model analysis, it gets even deeper than just the energy levels. There is a fundamental structural mismatch between the 2 mirror nuclei.
Yes, and this is where we have to look at the quantum shape of the atom itself. In quantum mechanics, atomic states are defined by a property called spin parity, denoted as J-pi.
Right.
It is a fundamental quantum identifier that basically dictates the total angular momentum and the spatial symmetry of the nucleus. The theoretical models, backed up by the experimental angular correlation data we talked about, demonstrate that the spin parity of the aluminum-20 ground state is 1 minus.
Okay, 1 minus.
But what is the spin parity of its mirror twin, nitrogen-20?
The ground state of nitrogen-20 is definitively 2 minus.
So not only is the total energy wrong, but the fundamental quantum shape, the angular momentum of the atom, is literally different from its mirror twin.
Completely different.
But wait, earlier you said the strong nuclear force doesn't care about charge. The shirts on the seesaw don't matter. So if the strong force is blind to the protons being protons, why is the symmetry breaking so drastically?
To explain this, the theorists introduce a crucial quantum phenomenon called the Thomas-Ullmann shift.
The Thomas-Ullmann shift. Okay, what is that?
It has to do with the spatial reality of a proton that is barely holding on at the absolute edge of a nucleus. In aluminum-20, the final, highly unstable valence proton resides in what is called an S1/2 orbital. This is an S wave state.
Let's try to visualize this wave state, because usually we're taught to think of protons packed really tightly in the center of the atom in this dense, hard little sphere, right?
The classic model.
But an S-wave orbital is different. Most orbitals, like P or D states, they have angular momentum. They spin, which creates a sort of centrifugal barrier that keeps the particle somewhat contained. But an S state has zero orbital angular momentum.
None at all.
So there is no centrifuge effect keeping it tidy.
Exactly. Because it lacks that centrifugal barrier and because the proton is so incredibly weakly bound to begin with, its quantum wave function, which is the probability cloud of where the proton actually exists at any moment, extends far, far out spatially from the dense core of the nucleus.
Like it stretches out.
Yes. It essentially creates a massive diffuse halo around the atom. The proton is basically spending a significant amount of its time far away from the center.
Okay, so we have this proton halo hanging way out in empty space. How does that break our seesaw?
It all comes back to the Coulomb barrier.
The electromagnetic repulsion.
Yeah. Normally, a proton feels a massive, concentrated amount of electromagnetic repulsion from all the other protons packed tightly inside the core. But because this specific halo proton is in this extended swave state, hanging way out on the periphery of the atom, it actually doesn't feel the full concentrated brunt of that Coulomb repulsion.
Whoa, it's too far away to feel the full force of the magnets pushing it away.
Precisely. The lack of a strong Coulomb barrier for this specific extended spatial orbital actually reduces the expected Coulomb energy of the entire nuclear system.
Wow.
Because the total electromagnetic energy is artificially lower than the standard models predicted, the overall energy state drops compared to its tightly packed, neutron-heavy mirror, nitrogen-20.
So it's literally a spatial geometry issue.
Yes. That sudden drop in energy caused by the extended wave function of this orbital is the Thomas-Ullmann shift. And it is the direct physical cause of the breakdown of isospin symmetry in aluminum-20.
Okay, so you listening might be thinking, if the rule is broken, does that mean our fundamental understanding of physics is just wrong? Like, did Heisenberg mess up the foundational math of the strong force?
It is a valid concern when foundational models fail to predict reality. But the fundamental concept of the strong force isn't wrong. What the Thomas-Ullmann shift in aluminum-20 tells us is that our models require entirely new, refined parameters to describe the subtle interplay of forces when nuclei exist in these extreme, unbound states.
So we just need to update the math.
Right. The strong force still dominates. But at the ragged edge of the drip line, where the binding energies basically approach zero, the electromagnetic force and quantum spatial effects like these halo orbitals start playing massively outsized roles.
We just can't use the standard simple equations anymore.
Right. The models need what we call charge symmetry breaking terms, explicitly added to the Hamiltonian equations to account for this. It's not that the old rules are wrong, it's that we are finally testing them in environments so extreme that the subtle microscopic exceptions become the dominant structural features of the atom.
It's like finding edge cases in a computer program that crashed the whole system.
A perfect way to look at it.
So aluminum-20 proved that our models definitely need adjusting. We have to factor in these massive extended proton halos, continuum coupling, and the lowered Coulomb energy. But what happens when theoretical physicists take these newly adjusted state-of-the-art models that actually account for the weirdness of aluminum-20, and use them to predict the next impossible atom?
Oh, it gets wild.
Yeah, when I read the paper detailing the gamma shell model predictions, it felt like staring into the mathematical void. They turned their attention to silicon-20.
Silicon-20 is where the theory truly pushes the boundaries of imagination.
To put silicon-20 in perspective for a second, stable silicon, the stuff in your computer chips in your phone, is silicon-28. It has 14 protons and 14 neutrons. Perfect balance.
Deal.
Silicon-20 has 14 protons and only 6 neutrons. That is an absurd, violently unstable ratio.
It is an absolute extreme system, and the researchers modeled silicon-20 using the Gamma shell model. As we discussed, standard harmonic oscillator shell models assume a nucleus sits in an infinitely deep, safe well. But the Gamma shell model is uniquely suited for the drip line because it operates in the complex energy plane.
What does that mean practically?
It successfully handles both the internal correlations of the nucleons and the continuum coupling seen in unbound nuclei.
Meaning it accurately calculates how the atom interacts with the empty space it's about to decay into, because it's essentially an open quantum system.
Exactly. The model treats silicon-20 as a somewhat stable oxygen-14 core, completely surrounded by 6 extremely unstable valence protons.
And the prediction, the model predicts that silicon-20 is a candidate for a staggering 6-proton emission. 6 protons.
At once.
Not sequential one-by-one decays like aluminum-20, but an explosion of 6 protons simultaneously. And the calculated decay energy is massive, 10.152 MeV. But the paper also notes a decay width of 371 keV.
Yes.
Wait, decay width? I know we measure energy in electron volts, but what does the width tell us here? Why aren't they just giving us a lifespan in microseconds or something?
That is a deep quantum mechanics concept tied directly to the Heisenberg uncertainty principle.
Oh, Heisenberg again.
Yep. In the quantum realm, there is an inverse relationship between the uncertainty in a particle's energy and the uncertainty in its lifetime. If an unbound state exists for a very long time, its energy is very sharply defined. It has a narrow width. But if a state decays almost instantly, its energy is highly uncertain. It spans a broad range of values. That broad range is the decay width, denoted by gamma.
So a wider energy spread means a shorter life?
Precisely. A width of 371 keV is incredibly broad. It mathematically translates to a lifetime that is unimaginably short. Silicon-20 effectively ceases to exist the exact moment it is formed.
So how do you even begin to look for something that spits out 6 protons instantly? Like, practically speaking, in a lab?
Well, the Physics Letters B paper actually proposes a specific experimental pathway. It builds on previous successes. Researchers previously created the 4-proton emitter magnesium-18 via a 2-neutron knockout reaction from a magnesium-20 beam.
Okay, so they've done similar stuff.
Right. So the theorists propose producing silicon-20 by taking a beam of silicon-22, which has recently been confirmed as a bound nucleus, and smashing it into a beryllium target to trigger a sudden 2-neutron knockout reaction.
Just ripping 2 neutrons right out of it in mid-flight, leaving those 14 protons completely unsupported by the strong force. But the structural weirdness of silicon-20 goes way beyond just the 6-proton explosion, right? There is this fundamental concept in nuclear physics called magic numbers that this atom just seems to completely ignore.
This is perhaps the most profound theoretical insight from the entire Gamma shell model analysis. In nuclear physics, protons and neutrons arrange themselves in specific energy shells, very similar to how electrons orbit in shells around an atom.
Okay, like concentric layers.
Exactly. And when a nuclear shell is completely full, the nucleus gains a massive amount of extra stability. The specific numbers of nucleons that perfectly fill these shells are universally known as magic numbers. And 14 is a recognized magic number for a subshell closure.
So, logically, because it has exactly 14 protons, silicon-20 should have a degree of inherent structural rigidity despite being unbound. The magic number should protect it somewhat.
It absolutely should. But the Gamma shell model predicts that the first excited state in silicon-20, the 2+ state, sits at a surprisingly low excitation energy of around 1.7 MeV.
Why is that surprising?
In nuclear physics, a low energy for the first excited state is a glaring, definitive indicator that the magic number has failed. The Z = 14 subshell closure has completely disappeared.
But if 14 is a universal magic number, how can it just stop being magic? That doesn't make sense.
The physical mechanism is called continuum-induced deformation. Because the nucleus is so incredibly weakly bound, it couples incredibly strongly to the unbound continuum, which is the vast phase space of free particles outside the nucleus.
Okay, so it's interacting with the outside void.
Yes. This intense continuum coupling fundamentally alters the internal energy architecture of the atom. It physically shrinks the energy gap between 2 specific proton orbitals, the S1/2 orbital we discussed earlier and the D5 orbital.
And when that energy gap shrinks, the orbitals start bleeding into each other.
Yes. Orbital mixing occurs. And when those specific orbitals mix, it drives a massive physical deformation of the entire nucleus.
So it changes shape.
drastically.
Yeah.
The atom radically warps out of its standard spherical shape into an oblate or prolate shape, like a flattened disk or a stretched cigar. That extreme spatial deformation completely obliterates the geometric stability of the closed shell.
Picture the magic number shell as a perfectly built, incredibly sturdy brick wall, right?
Okay, a brick wall.
If you have exactly 14 bricks arranged in a perfect dome, the structure is incredibly solid. It can withstand immense pressure from the outside. But then you expose that dome to the extreme weather of the unbound quantum continuum.
The storm of instability.
Right. The storm is so fierce that the mortar holding the bricks literally dissolves, the wall physically warps and bends out of its perfect geometric shape, and it instantly loses all of its magical structural stability.
It really makes me ask, is it even fair to call it silicon at this point if it has no magic shell stability, no spherical shape, and immediately throws away 6 protons? Well, from a purely elemental standpoint, the 14 protons dictate it is, by definition, silicon. But from a behavioral and structural standpoint, you are absolutely right to question it. It is a completely alien system compared to stable matter. It is basically a transient state of extreme quantum chaos that barely qualifies as a nucleus before it dissolves back into the continuum.
Wow. Which basically brings us to the ultimate takeaway of all this data. Today, you and I journeyed from the comfortable safety of the stable nuclear chart, where atoms play by the rules and sit neatly in their valleys.
It was a long journey.
It was. We crossed the absolute boundary of the Proton Drip Line with the validation of Aluminum-21. We witnessed the rule-breaking, sequential 3-proton explosion of Aluminum-20. And we explored exactly how its extended proton halo systematically dismantled the foundations of isospin symmetry.
The broken seesaw.
Right. The broken seesaw. And finally, we peered into the mathematical future, analyzing the prediction of an atom so deformed by its own continuum instability that it vomits 6 protons simultaneously, silicon-20.
And if we return to why this matters to you listening, investigating extreme open quantum systems like Aluminum-20 is not just atomic stamp collecting, it's not just cataloging weird stuff.
No, it has huge implications.
It is the only physical way we can probe the subtle, hidden interactions of the strong nuclear force, the electromagnetic force, and quantum mechanics at their absolute limits.
Because these forces are the underlying codes that ultimately govern all matter in the universe.
Precisely. When we finally understand exactly how symmetry breaks in a German particle accelerator, we mathematically better understand the chaotic heart of a neutron star spinning galaxies away.
It changes the whole map of the universe. Which leaves us with one final provocative thought. If Aluminum-20 proves that the fundamental rules of symmetry bend and break at the ragged edge of stability, and our best models are now predicting atoms that eject 6 protons in a single breath, what entirely new, unimaginable forms of matter might briefly flash into existence inside the chaotic, high-energy heart of a supernova long before we could ever hope to catch them in a detector on Earth? We'll leave you with that. Until next time, stay curious.